Hi everyone, welcome to part 3 of the MCP Security series. In the first part, we looked at a deep dive into the MCP protocol itself. Why is it required? What are its capabilities? How does it work, etc. In part 2, we explored a number of attacks on MCP where the MCP server or the MCP client is poorly implemented. We used both Claude Desktop and MCP Inspector as tools to play with MCP servers that are vulnerable. In this video, we are going to summarize all that we have learned and kind of go through a checklist of MCP security, which would be useful in either case, whether you're building an MCP server or you're building an MCP client. So let's take a look at summarizing everything in this kind of capstone video. We understood that when we have multiple MCP clients, API software like Cursor, Windsurf, Claude Desktop, and they need to talk to other servers like Slack, Jira, Confluence, Microsoft OneDrive, email, Gmail, etc. It can create an M into N connectivity code requirement. With MCP, it becomes an M plus N. The same interface works with any type of client on the user side. This has witnessed by the explosive adoption of MCP. In fact, just a couple of days back, when OpenAI had its dev day, it released Agent Builder, which heavily relies on MCPs within ChatGPT. So obviously, MCP is now the talk of the town. But the critical thing to keep in mind is when we go deeper into the MCP protocol, when we read its specs, a lot of these security aspects are left to the developers. It is left to your implementation of input validation, of limiting the scope of MCP clients and MCP servers. It is also left to how you interpret the system prompts and instructions and tool descriptions coming from an MCP server. And it is also up to you how you implement the OAuth requirement for authorization and authentication. All of this falls on your shoulders. We discussed about the three components of an MCP architecture: the host, the system on which the MCP client is running, the MCP client, which we used Claude Desktop and MCP Inspector as examples. And then you have the MCP servers, which expose three key primitives to the MCP client. They expose tools, they expose resources, which are files or API data, and they expose system prompts, which are useful for the tools to use to get more value from the MCP servers. We also saw that the servers have a way of talking to the clients, and servers have to be considered as untrusted. Tool descriptions could be a problem. Servers trying to do LLM sampling when they request the usage of the LLM from the client could be a problem. And when they request for structured data or additional data from the client using something called elicitation, that could also be a problem. And so servers have to be considered as untrusted. We looked at a vulnerability where we looked at a file manager, and instead of just doing a dir, we were able to do command injection. Now, I know that many of you look at these examples and think, oh, this is very contrived code. Who put shell equal to true? But 43% of MCP servers have been found to be vulnerable to command injection. And just today, I want to share this with all of you. Just today, we have Figma MCP being found vulnerable to this exact vulnerability, remote code execution. And if we go deeper into this, it even has a CV. The server introduces the possibility of shell meta character injection, precisely the attack that we explored in part 2 of this series of MCP security. And if you go deeper into it, it explains that after the initialization request, which is all fine, the client sends a JSON RPC request, which is the protocol used by MCP anyway, and calls the tool get Figma data or download Figma images. And within this piece of code, the fetch API executes the curl command via this child process.exec, and that's where the command injection happens. So this is precisely what we looked at. So it's a real issue, it's going to get found more and more. And as you test MCP servers, this is something that you will have to put on top of your list of issues to look for. We also looked at path traversal or directory traversal, where we put in dot dot slash and dot dot slash characters to come out of the root directory. This can also happen on in the Unix world with symlinks, symbolic links, which actually link to a different file from what the MCP server is expecting to provide to you as a resource. They can link to the password file on Unix, or the private keys, SSH private keys, or environment variables, etc. All of this can be problems if we don't do strict input validation, if we don't use the right Python libraries, if we use shell equal to true, and all of these kinds of bad programming practices. We also looked very interestingly at prompt injection. When we think prompt injection, we are usually thinking, as a user, I'm trying to inject prompts onto a server application that supports AI, that uses AI. In this case, it's the other way around. The server can put additional instructions in the tool description. These would flow down to the MCP client, and from here they would flow into the LLM, and those instructions would get executed. In our examples, we used three very benign ways of doing things. We said, compose a haiku, or give us a tip, or give us additional facts. Did you know kind of facts about cybersecurity? Those kinds of interesting things, but they were not harmful. But you could see the flow in terms of where the LLM request flowed from the server to the MCP client and then to the LLM, and the instructions were actually executed. When it comes to MCPs, things start to get more complicated. Authentication could be a problem. You may not authenticate the user properly. Your OAuth implementation may be uh, problematic. There's also the concept of a confused deputy. An MCP server could be connected to multiple MCP clients of different users, and this MCP server might be talking to, let's say, Slack. So it would be acting like a deputy to talk to Slack, and it may confuse one user's request with another user's request. And attackers may use poor session management or poor ID creation, predictable ID creation, to confuse the MCP server and relay or parlay attacks or data of one request to the other user. So confused deputy is very much possible. Weak session management with the session IDs, as we saw in the response request. And supply chain attacks. So here we look at, for example, a malicious package called MCP Remote was actually published, and it had nearly 500,000 downloads before it was pulled off as a malware. But it looked like it would be the right package to use if you're developing MCP, and developers pull down these malicious packages and use them in their code. Rug pull attacks. The tools that an MCP server exposes um, are updated to the MCP client. If the tools change, the server has the option to update the client or not update the client. So a rug pull attack is where initially the tool starts off benign, but then it is replaced by a more malicious version, maybe by the MCP creator for nefarious purposes, and the MCP client has always approved it, and it gets executed. So that could be a big issue. Confusion and dependencies, just like the MCP remote package, you could be using third-party libraries that get infected or have similar names or confusing names, and you could have a supply chain issue there as well. On the client side risks and network risk, if you're building a local MCP server and you bind it to the IP address 0.0.0.0, it would get exposed to the entire network, local network. Whereas what you want is to bind it to the local host IP address, which is 127.0.0.1. Other issues we've seen: MCP Inspector, the software we use to test and investigate our MCP servers, itself had a CVSS 9.4 rated critical vulnerability, which allowed remote code execution. Configuration poisoning: for our Claude desktop, we use the config.json file. If this JSON file could get corrupted, attacker could load malicious MCP servers into your Claude desktop. So these are client-side attacks that can also take place. Zero trust is our principle always. You have to not trust anything coming from the MCP server. The MCP server should not trust anything coming from the MCP client. The client should validate requests and responses going both ways, so that malicious instructions are not being sent surreptitiously to the LLM and getting responded and data being sent back to the MCP server. Authenticate all requests. Authorization through OAuth. Perfect implementation is very important. Principle of least privileges, input validation, output validation, all of these standard principles of security apply. It's just that the attack surface has now expanded dramatically. We will go deeper into better and proper implementation of the OAuth 2.1 framework, which is a requirement with MCP. We're beginning to see improper implementations of the OAuth framework also leading to issues. And three basic rules are very, very important. Proof key for code exchange prevents authorization code interception attacks. Resource indicators binds access token to specific MCP servers. And protected resource mandate securely informs clients where they should go to obtain authorization, prevents attackers from redirecting the client to a malicious identity provider or authorization server. So we will go a bit deeper into this in future segments. Secure coding checklist for developers. In fact, I would like you to point you to a very nice blog post from our friends at SemGrep. I will put a link to this in the description of the video. So this is the blog. It's well worth reading the whole blog. And then they also have a checklist linked in this. And here is the checklist. Excellent checklist. If you're building an MCP server, what transport mechanisms are you using? If not HTTPS, why not? Network bindings we spoke about. Server doing origin validation. Is the server authorized? Authorization implementation. How are MCP features being properly implemented? We spoke about elicitation when the server requests more data from the client, sampling when the server sends a request through the client to an LLM. Routes, the restriction that the MCP client enforces on what paths or what folders the server can request data from. So that should be properly implemented. So on and so forth. So this is a great, if you do any path related operations, are you using the right libraries? Are you doing proper input validation to prevent directory traversal? Shell operations, are you using the command shell or some other better way to do it? Or have you ensured that shell equal to true is not enabled? Plus, have you done input validation on anything that could get injected from a user end into those shell operations? Any request basically where you process using customer or user input is a problem. So all of that needs to be very thoroughly validated. On the client side, does the client support routes in terms of the restriction of resources on the local system? Does it properly implement that routes functionality? Does the client support sampling? Very interestingly, we saw that Claude Desktop does not support sampling. Does the client have any special handling of sensitive data, elicitation, etc.? So this is pretty much a good or a pretty comprehensive checklist for MCP, and I'm sure that this will evolve as things progress. So this is just a summary of it. Shell equal to true, bad idea. Use parameterized queries anytime you're going to run an SQL uh, command based on user input. Canonicalize paths before validation to resolve symlinks and relative paths and then validate the result. Implement strict JSON schemas, never hardcode any credentials, obviously. Uh, don't bind to 0.0.0.0, bind to 127.0.0.1. Run everything in containerized sandbox environments. Ensure you have comprehensive logging and monitoring. Disable auto updates. Implement proper network segmentation and firewalls in case the MCP service is hacked, the user cannot penetrate deeper into your network. Install code only from trusted sources. Do a review of the source code if you have access to the source code. scrutinize the permission requests, keep everything updated, and never enable anything that is an always allow kind of parameter. So this is where we are, friends, with MCP. It's extremely popular. It's very widely used. 43% of MCP servers are found to have command injection. 437,000 downloads of a MCP remote package, which sounds and looks legit but turned out to be completely malicious. The MCP Inspector software itself had a 9.4 level CVSS score bug, and a lot of the security requirements in MCP depend on you as the developer, whether you're developing MCP enabled clients or MCP servers. So this is a detailed action plan. Audit all your existing MCP servers, run them through a secure coding tool, implement proper authentication and input validation for everything coming from the user, review third-party dependencies if you're using, validate your supply chain, set up obviously DevSecOps, automate your security testing in the CI/CD pipeline, document security assumptions and threat models for your tools. If you are somebody that's operating MCP servers in your environment, scan and document all MCP servers that exist, catalog their permissions, tools, resources, prompts, fix your network bindings, review and revoke excessive tool permissions, implement monitoring and alerting for suspicious agent behavior, and establish a governance process for vetting new MCP tools before deployment. And finally, for users, review your installed MCP tools and remove anything that you don't trust. Revoke unnecessary permissions. Enable confirmation prompts for all tool executions. Stay informed about the latest in MCP security and report suspicious tools to maintainers immediately. So, folks, I hope you found this coverage useful, and please share, like, and subscribe. And please add in the comments what kind of MCP security issues you've been seeing out there in production and what kind of content you would like to see further in this course. Thank you for watching.